No hashes, no blockchain security. Here are five properties that make them rock solid. This is Tech Under 5, where tech meets simplicity in just under 5 minutes. Today, we'll dive into cryptographic hash functions, why blockchains rely on them, and the five properties that make them bulletproof. So, what is cryptographic hash function? A cryptographic hash function is a mathematical function that takes in any input value and converts them into a fixed size message called a hash. Imagine it like a digital fingerprint. If you input a value to the mathematical function, it will always result in the same output. And the best part is that it's virtually impossible to guess what the input value was just by knowing the output. Let's illustrate this with an example of a toy hash function, which is sum of bytes of x mod 10. This function outputs a single digit from 0 to 9. Let's take an example of ABC string, which is 294 mod 10 and gives an output of 4. Many different inputs will land on the same digit, lots of collisions, because the output space is tiny, only 10 possibilities. But for a hash function called SHA-256, which is what Bitcoin uses, if I enter the input as mouse into the SHA-256 function, it'll give a fixed 256-bit output which would look something like this. And changing just one character with a capital M, and you'll get a totally different 256-bit output, something like this. The possibilities are huge, which is in the range of 10 raised to the power 77, more than billions of billions, unlike the toy hash function. Now take that behavior and apply it to a chain of block, and this is where hashes matter. Blockchains stitch data together with hashes to make tampering obvious and expensive. And this brings us to why hashes matter in blockchain. Each block stores the hash of the previous block. And so if you change anything in the old block, its hash will change, as well resulting in subsequent blocks having mismatch in the hash value. This makes stamping obvious and expensive, since for you to change data in one block, you will have to make sure that you change data in all the subsequent blocks, which is honestly extremely expensive. And that expensive part isn't magic, it's built on five properties that you need to know. Hash functions are deterministic. Same input, same output always. This predictivity lets every node independently compute and agree on the same hash. Second is the pseudo randomness, also called the avalanche effect. Hash results look like random gibberish. Change even one tiny little thing in the input, and the result becomes a completely different string. You cannot predict it. The only way to know the hash is to run a hash function. It is also a one way function. Given a hash, it's infeasible to recover the original input. That's why hashes are used for integrity checks and security. It's incredibly fast to compute. Hashes are designed to be quick. Miners can verify blocks and transactions rapidly. For example, in Bitcoin, miners need to compute billions of hashes per second while searching for a solution. And lastly, it is collision resistant, which basically means that it is computationally infeasible to find two different inputs with the same hash. With 256-bit hashes, the search space is astronomically large, 2 raised to the power 256 options, that is billions and billions of search space, making deliberate collision effectively impossible with the current tech. So, in short, hashes make a tiny fixed ID for any data. Same input gives the same ID. Tiny changes explode into a new one, you cannot reverse it. It's quick to compute, and two different inputs almost never match. That's exactly what blockchains need to stay honest and easy to verify. This is Tech Under 5, where we make tech simple. If you liked what you saw, hit that subscribe button and see you next time.